Hello, everyone, and welcome to another We Save Structures design series webinar from Vector and BCS Engineering. Today we are doing discrete galvanic anode design. So this is going to be kind of a how-to on how to use discrete galvanic anodes for repair, corrosion control, and a little bit on new construction. So this year we are celebrating 25 years of GalvaShield. So what's excellent is our presenter here, George, brought to market the very first galvanic anode for corrosion control and reinforced concrete. And so he's actually going to be showing us some of those projects and some of the research that he's gathered over those 25 years. And so that's kind of the goal of this whole series, is to use that 25 years of learning and innovation to help educate the industry about all the lessons that we've learned over the years and how we've used that to better design products and teach you how to better design your protection systems. And join us for our next session. It is May 29th with Cheyenne Yazdani from BCS Engineering. He's going to be diving into using a different category of galvanic anode known as a distributed anode system. You can find that on our website at wesavestructures.info, same place you would have found George's webinar here. And we have a challenge to everyone that is present. We have a question competition. So all you got to do is put your questions into the Q&A function that you'll see here in the Teams live events. We ask that you do include your name when you are leaving your comment, because our system does not track who is coming, so you'll have to manually give us your name. You can ask as many questions as you want, so ask away. And the best question is going to win a $100 Amazon gift card picked by our presenter here, George. And one final mention before we pass it over to George is we want to call out our environmental impact calculator. So this is a calculator we've got on our website at wesavestructures.info. And so what you can do with this is visualize, calculate and visualize, the difference that you're making in sustainability by preserving concrete. So all you got to do is enter in, the volume of concrete that you have preserved by keeping a structure in place or separate elements. And then it'll calculate all the different resources that were maintained or preserved, as well as, the energy and all that. Creates a nice PDF that you can keep for yourself or share with your friends. And finally, it is time to introduce our speaker, Dr. George Sergi. You can see he's got quite a bit of letters after his name there. He's spent a lot of time researching and educating the world on cathodic protection and different ways of increasing the durability of concrete throughout the years. You can see all the different associations and such that he's been involved with, and how he's been published quite a bit throughout the years. And you'll get to learn a little bit about what he's done coming up right here and now. All right, George, take it away.
Thank you, Ben. Thanks for the introduction. I'm going to be talking about galvanic anodes, quite obviously. But the lucky thing really here is that we've now got 25 years worth of results from the very beginning that we first installed anodes. And then we were then able to look at all these results and gain some key information. And from analysis of all that information, we were able to establish a much improved design procedure. And it's this design procedure eventually that I'm going to get to after talking about how we used the results from the beginning. Okay, and the main takeaway I want you to take from today really is the design procedure of any type of anode. I mean, I'm talking about our particular anodes in this case, but any manufacturer, anybody who produces anodes should really based their design procedures or suggested design procedures totally on the performance of the anodes, not on guesswork, really. So here are the 25-year results I was talking about. This is a specific crossbeam that we looked at in Leicester in the UK. We had about 12 anodes installed in 2 adjacent patch repairs. You can see the anodes as they're laid out. The anodes were positioned in such a way that we could take the current through a junction box, a monitoring box, before it went back to the steel reinforcement. And we were therefore able to intercept it and take readings. Current obviously was the most important one, but we also did potential readings and depolarizations and so on. But the main result I want to talk about here is the current and how that varies with time. And this is extremely useful information that we gained. If you plot the current density, or just the current, versus time in a logarithmic scale, we can see that we establish pretty much a straight line. So the current diminishes in a exponential way, a constant way, which is very fortunate for us because that means we can predict current in the future, provided we have a constant reduction in the current. In this case, we got the information that we got from that graph is that the current halves every 7 years. So year 7, we had half the amount of current. Year 14, half again. Year 21, half again. And in this case, that what we call an aging factor from that information turned out to be about 7 years. So we had 7-year aging factor. Now, the other thing that we managed to gain from this particular setup was that at around 15 or so years, we saw a little crack developing on the side here, and therefore realized that possibly we weren't delivering enough current at that stage. So we marked that as the minimum current requirement, which is 0.4 milliamps per meter squared. And experience also tells us that that's just about the right level, depending on your risk of corrosion. This is was a low risk, low to medium risk. So remember that number, 0.4 milliamps per meter squared. The spacing here, you can see, was quite wide. It turned out that it was much wider than we normally do now. So that's about 600 millimeters. With current calculations, it actually falls at about 400. So we had overrun the anodes at the beginning. And this is what happens actually when you overrun anodes. This is the middle one that I showed before, at nearly 7 aging factor of about 7 years. There was an even worse one, a column across the other side of the bridge. In there, we had anodes spaced at 750 millimeters, and they behaved even worse. They started off with a very extremely high current density, and the reduction was much more pronounced. 5 years down the line, we thought, okay, let's do another one on the same structure again. A new area developed that was corroding, did a patch repair, and used larger anodes, XP2 anodes, which have got the twice the surface area of the XP, the original XP. But we also decreased the spacing to 300 millimeters, which was more appropriate this time round. And you can see that it started at essentially the same current as the others. But because we are not pushing the anodes anymore, they are lasting a lot longer, and you have a much improved aging factor, so far of the order of about 16 years, which is a huge improvement in performance. Now, we've taken kind of an average of a lot of other structures that we've been monitoring as well, and that's around 12.6 years as an aging factor. And we use that now as our standard for calculating and for designing. The other things that we've learned from that side is that we've taken out anodes at different times, 2 anodes at 10 years, 2 anodes at 20 years, and all 6 anodes of the column, because they'd sort of almost died out. And we analyzed those. We looked at them, taken away the corrosion products, as you can see on the left side, it says as it came out from the structure. A lot of buildup of corrosion product, which had replaced the zinc that was in existence previously. And then we removed that oxide layer, which is a layer of zinc oxide, and end up with a clean core of zinc, which is pretty even. You can see that the corrosion was quite even over the years, even after 25 years, but there's still a lot of zinc left, and that's really by design. Especially now that we've learned a lot more, we could explain that away quite easily. We have worked out an efficiency because there's a theoretical amount of zinc that you should be consuming based on the current output of the zinc. Now, we've been monitoring the current, therefore we could work out in theory using Faraday's law how much zinc we should have used, then weighed the anode, and therefore found the actual amount of zinc that we used, and the ratio is the efficiency. So you have 75% efficiency, which means 75% of the anode was used to deliver the current, the rest of it was just self-corroding. So we established an efficiency, a very important parameter. And the next thing that we managed to find was the current. You saw earlier that the current was going up and down. That is very typical of summer and winter readings. And if we plot current output as a reciprocal of temperature in Kelvin, or the logarithm of current output, we get a straight line. This is on site in Ohio. This is in the lab, and you can see that it's pretty straightforward, a straight line. It follows the Arrhenius relationship, which tells us that every 10 degrees you get a doubling in the current, or every 10 degrees going downwards you get halving of the current. So that's another interesting feature. This is quite a known phenomenon really from corrosion. Corrosion increases every 10 degrees roughly. So we're now seeing that the anodes themselves do exactly the same thing. So the inference of that is that as the corrosion current increases, therefore requires more protection, but the anode is able to provide that protection by increasing its current output as well. And that temperature is really quite an important parameter also to be taken into consideration, not in terms of whether you've got the right level of protection, but as to how much zinc you're actually using in the process. So what we have done is taken an average for all our readings in the UK, for example. The average for the year is 10 degrees. So we're basing current output and exact current output on 10 degrees temperature. And if you have 20 degrees, then you know that your current output will be double. But as I said, the corrosion rate would also be double. But up to about 15 degrees, it works out that the XP anode that we have designed is ideal. It has a enough surface area for the current output to be the right amount. Now, if you want a higher current, you need a larger anode, not in terms of surface area. The surface area remains the same because that's the controlling parameter that gives you the ideal current, but you need a much bigger volume because you are consuming the zinc at a much faster rate. Therefore, you need a bigger anode. So we've developed the X range of anodes. So for the standard situation up to 15 degrees, we have the XP range, and for the higher current outputs, which anything above 15 degrees into the 20s, 30 on average. I mean, you can see the highest temperature really very rarely exceeds 28 degrees. That's as hard an environment as you can get in the Middle East. So we've now got the XPX range. Like I say, same surface area, but twice the volume or mass of zinc to compensate for the additional rate of zinc consumption. Okay, so in our specifications, we've got example specifications that I can show you a bit later. We have to be stating that our activator is alkali. We need to state that our efficiency is 75%, and so on. And we need to back up all that data with information as I've been showing, but obviously show you a bit more information from other structures as well. There are obviously other activators. There are still alkali activators probably being used, but their performance may not be the same as our anodes. We know what the performance of our alkali activated anodes. We know what our alkali is. It's saturated lithium hydroxide, which gives you a constant pH, and if you can maintain that lithium hydroxide content at saturation, you will get the same performance from the activator. So it's the reduction in primarily the reduction in the surface, the zinc, and therefore the surface area that diminishes the current. There are other things, but that's primarily the reason. Halide activators tend to have a lower, in fact, considerably lower aging factor. And if a manufacturer doesn't give you an efficiency, for example, then you have to assume 50% out, I think. So the important parameters for designing a good galvanic anode system is to know the activation. Is it good? Is it alkali, and is it good quality alkali, if you like? Does the alkali last the period of the design life? What is the aging factor? How does it age? How the current diminishes with time? The expected current delivery of the anode at in our case 10 degrees. That's normally related to the surface area. The efficiency, as I mentioned, is obviously important because you need to have enough zinc of the right surface area at your design life to be able to produce the current that you require. And you need to establish that minimum current density requirement at the end of the design life, not the beginning. So at the beginning, it will be considerably higher. But what you're interested in is my current density enough at, say, year 20, if that's the design period. And this is a sample specification. We've got it on the website. It gives you an example of what you're looking at. I've taken a few extracts from it just to show what sort of information you can find. Now, what we've done that's also very, very important is looked at our past performance, looked at the what's available in the literature, and came up with categorizations. So based on some work I did at the Building Research Establishment, for example, the chloride level up to about 0.8 is classified as a low to moderate risk of corrosion. Even if you don't have sufficient chloride concentration data, you can have a reasonable estimate of what your corrosion rate is, depending on the conditions, the exposure conditions. Obviously, no marine environment in this case. High categorization will be if you assume that the rate of corrosion may be significant, and if you know the chloride concentration is up to 1.5%, and then there's the extremely high, obviously, which is above 1.5%, and it could be a marine environment, for example. And based on our own observations, once again, but also from work by some Italians, Bertolini et al. From Milan, who did very good experiments in the lab. They're actually the people who initially talked about cathodic prevention or corrosion prevention, how to prevent corrosion from happening, keeping the current at relatively low levels. And they were able to find that up to 0.8 milliamps per meter squared. I've already talked about 0.4, and that sort of is consistent with their work as well. But up to 0.8% chloride, you require of the order of 0.8 milliamps per meter squared to avoid initiation of corrosion. But the very high level of corrosion risk, which we call extremely high, which will be higher than 1.5%, they actually, in their experiments, they found that holding the current density at 1.6 milliamps, they were able to extend the life before corrosion to beyond 5 years. Their experiments are 5 years, so we don't know. Obviously, they finished the experiments. We don't know whether it would have lasted longer than that, but it did, up to 5 years. They dismantled the samples and analyzed the amount of chloride that was around the steel at that time, and they found that they had about 3% chloride, yet no corrosion. So the steel, simply by exposing it to 1.6 milliamps per meter squared over that period, was able to resist corrosion. So something positive was happening over the years, and I'm going to talk about that further down the line when I talk about new construction. Okay, now, what are we talking when we say current density in a patch repair? I mean, the obvious thing to think is that you've got you calculate your area that you're protecting, and it's the average current that flows in the area. Well, actually, that's not the case, and it's a little bit more complicated than that. What we always ensure is that we have a current density delivered at 100 millivolts outside the patch repair, or 100 millivolts from the edge of the repairs, like at this red crosses, which is the minimum current density. So if we want 0.8 milliamps per meter squared, it has to be at those points, a line along all the steel that's at that position. In order to do that, we used a model, basically, as I've shown you here on the diagram. That's our model, and obviously you're going to get current delivered from adjacent anodes, and therefore it's the additive kind of amount of current that you get to that point. But the average current density elsewhere is likely to, over here, is going to be much higher, and it's kind of double down here. So if you were aiming for 0.8, you probably get 1.6 down there, and if you take an average, it will be somewhere in between the two. So it's not quite right. But what I found just by messing around with numbers really is if I take an area which is double the spacing in one direction and times one the spacing in another direction, and find the amount of steel that's within that area and design the current density for that, then I am within 20%, within a 20% area of the required current density. So it's a rough estimation, and if you sort of don't trust our tables that I'm going to show you later, you could do a rough estimation like that and see whether that's true or not. Okay, there's some very important information that I found that people from Germany have done. Helm and Raupach in Aachen University, they used our anodes, they borrowed our anodes, and they used them in certain experiments, electrochemical experiments, to determine their behavior with different potentials, different resistivities, and so on, and worked out numbers which they fed into their model. And their model considered as a square slab 4 times as big as what I'm showing you here. If you consider that to be the center of the slab, then obviously you've got 3 more quarters to complete the slab that they used. They have 2 layers of steel reinforcement, roughly, well, just below a steel density of less than 1. I'll show you how steel density is determined later. And then they lined the patch all the way around with anodes. But of course, in their plots, they've got that line there. So it's from the center of the patch all the way to the edge of the slab. And this is a summary of the results. That they've got a very busy graph, but I'll aim to explain as best as I can. Originally, you've got an area here which is in which the steel is corroding. That's the center of the slab. That's the edge of the slab over here. This area has no chlorides, or not. That's not true. That's assumed to have a lower level of chloride, and this has a high level of chloride, which induces corrosion in the center. And if you look at the potential map of that, then it's that red line. So what you're doing here, because if you've got a corroded region with a low potential, you're actually dragging the potential of the steel outside the patch downwards. Now we know that pulling the potential downwards is really the definition of cathodic protection. So you are cathodically protecting this region here, and therefore no corrosion occurs, or the corrosion is occurring within that region. If you do a patch repair and don't put any anodes in, you modify that potential map, potential gradient to this top line. So now you've done the opposite. Rather than protecting that region, you are forcing it to corrode. You're producing the opposite of cathodic protection. You're producing anodic destruction, if you like. And that's why eventually we get corrosion on the outside of the patch. This is the theory about incipient anode formation, or the ring effect. And what we are trying to avoid is that ring effect. Therefore, we put anodes inside the patch. This is now the anode. And these lines show increasing numbers of anode, or reducing spacing of anodes. So at 670 millimeter spacings, they've done something, but not very successful, really. That's still pulling the potential outside in an upward direction, and it therefore won't work. The next level at 64 millimeters spacing between anodes, you've got a reasonable drop in your potential, which in most cases that might be enough. But to be sure, you really need to be going at least at where that red line was initially, or a little bit below. So the little bit below here is this particular one at 246 millimeters. So theoretically, they worked out a spacing that will be sufficient for this type of environment. And thankfully, it ties up with what we do. Now, what you've noticed also is that most of the effect is within 100 millimeters from the edge of the repair. If you want to achieve 100 millivolt depolarization, well, you can do it only a little bit. This is the line that tells you that you got 100 millivolt depolarization. So it's basically that minus 100 millivolts. And you can see that you can, no matter how many anodes you put it at a very, very tight spacing, 36 anodes, so 80 millimeters, you can only get to there. So that's however not the purpose of the anodes. The purpose is to simulate that type of behavior. So you put a big anode in the patch repair to replace the original anode that was the corroding steel, to stop corrosion from occurring outside. So 100 millivolt, 100 millimeter outside the patch repair is really all you're concentrating on, which is what I explained our model to be. And this is the level that was predicted by the Germans. And that's exactly the level that we have, 250 millimeter spacing at just under 1, steel density of 1. Of course, if you've got a denser steel, not denser, but more steel per unit area of concrete, you would need to decrease your spacing. Or alternatively, you use a larger anode. XP2 has double the surface area of an XPT. XP4 4 times the surface area, and therefore you're able to increase the spacing of the anodes in your patch repair. Okay, so these tables are based on, for this particular one is for a high risk, which is 0.8 to 1.5% chloride. It's for 20 years, and it's 100 millimeters away from the edge of the patch, and is the table that applies to that. There's other tables for each of the risk categories. So the low, medium risk, high risk, and extremely high risk, and that's all in our data sheet. But like I say, you could estimate it roughly by just doing what I did before. I don't want to go through it again. Okay, steel calculation. I'll go through that quickly. Really, you look at how much steel is exposed in your patch repair, and you measure the length of the steel and the diameter of the steel. So it's length times diameter times pi times the number of bars that are the same size, and you divide it by the exposed surface area. In this example, it's just 1 square foot. Yeah, but it could be 1 meter squared, it could be 2 meters squared, it could be 1.5 meters squared, whatever. So it's all the steel in both directions. See the length of the steel bars. And if it's a square, obviously the length would be the same in both directions. So you multiply up for the number of steel bars. Just a quick example, really. If there's bar 1 going in one direction, 12 millimeter, the length of your patch is 1 meter, then that gives you 0.094 meters squared. If the other one is at 100 millimeter space, so this is the spacing of anodes. It gives you, obviously, this different number of anodes, so you get a different area, add up all the area, and then you add 10% at the end, because you're not simply because of error, but because you're trying to take the current outside the pass repair. So you need to take that into consideration. Okay, so there's a typical repair, if you like. There's a square. You measure all those bars, the area of all those individual bars, and that gives you the steel density. You divide the surface area that you've exposed by the area of all these steel bars. I imagine that to be quite a high steel density of over 1. And then you measure the perimeter, divide by the current, well, the spacing that you've achieved from your spacing charts, and that gives you the number of anodes that you need to set out at the perimeter. Same if it's a straight line, if you like. I mean, the perimeter is measured along here. So that gives you the number of anodes that you need to install. In a lot of cases, once you start setting your anodes out, you might find that there's a gap somewhere. You need for another anode. That's obviously down to personal judgment. For CC anodes, it's a little bit easier actually, because all you're doing is drill holes at constant spacings. Once you've worked out your steel density inside the concrete by using your whatever you use to measure your steel spacings and diameters, you are able to find a steel density. You work out the number of anodes that you require, and you spread them out in a constant grid function. Now, you'll notice here that we have a much denser area of anodes. The reason for that is that because there's a lot more steel in this area around the column that there is over here. But the reason may not be just that. It could be that you have a higher risk area where you know that your chlorides are higher, and therefore you need to space out the anodes much closer together. So that if that column wasn't there and we had that sort of density of anodes, that means that there's a different zone. It contains different levels of chloride. And for the CC situations, the corrosion control, you're not simply trying to prevent corrosion, although in most areas that's exactly what you're doing. There'll be areas where corrosion may have already initiated. The risk is high. You haven't really broken away to see if there's any corrosion. You would assume that there is some corrosion already occurring, so you would need a higher current output or a higher current density. But again, if we assume an aging factor, 12.5 years here, mean temperature 10 degrees, design period 20 years, efficiency 75, I've been through that already, concrete resistivity 20 kilo ohms, and you do your calculation, you will find that the current diminishes obviously with time. This is the current that you achieve per anode at year 20. It's about 82 microamps. And the amount of zinc that you consumed over that period, based on efficiency of 75, is of the order of 30 whatever, under 40 grams. Now, there's a lot more zinc in that. As I showed you before with the samples that we've taken out from the bridge, often there is about half of the zinc still remaining. So here we predicted that we're going to use only 37% of the zinc. Now we want the zinc obviously to have a surface area at that stage to be able to produce the current that you require. So if they tell you, if a manufacturer says I've got enough zinc to last you 20 years, or to last you 50 years. That's not the life of the patch repair. That is, it's able to produce current for that time, and theoretically this can produce current for probably 100 years before it's totally consumed, but the current is not going to be enough. So you need to know what the current output is when the surface area is a certain level, and that's what that predicts. Basically, at 20 years, this is the surface area that I require to produce the minimum current that I want. Okay, now, as I said, because there's more likelihood of corrosion when we use the anodes for corrosion control, we've increased the level of current that you require. So at less than 0.8% chloride, we're now talking about 0.6, then 1.2, then 2.4 at the higher end, and that sort of works out at what was that? About at least 9 or so milliamps per meter square at the beginning. Okay. We've also produced, although it's easier to work out a current density because it's normal square, so many anodes equally spaced out, and you take the average of the current delivered to the whole structure that you're protecting. We've also produced tables for people who want to use them. Once again, we're talking about decreasing spacing for increasing steel density and so on. And this individual tables for each of the risk categories. The X range in this case has the equivalent surface area of a CC4, the larger of the anodes, but it's got a lot more zinc than the CC4, and that's because you will be using it at a higher temperature, as I explained before. You will be consuming it much faster, but you need to get to that same stage where at say 20 years, you still have the right amount of surface area to be producing the current that you require. Okay, now I'm going to go a little bit through very quickly, really, on design for new construction. In order to appreciate really, how anodes work in new construction, you need to understand the benefits that you get from any type of polarization of the steel. In summary, really, you've got an increase of alkalis and a decrease in chlorides around the steel. Both are beneficial. You have, as we've seen before, with the work at in Italy, you have an increased tolerance to chlorides, and you have a buildup of alkali phases on the steel concrete interface. I'll go through each of that individually slightly. Here's a model really of cathodic protection or polarization. Just concentrate on this side where the steel is. Whichever reaction actually happens, whichever cathodic reaction happens, you are producing hydroxyl ions. That's the end product. So plenty of hydroxyl ions. You're also dragging calcium, sodium, potassium ions being positive. They get attracted to the steel, which is negative. So you end up with calcium, sodium, potassium hydroxides. You're also pushing away the chlorides, sulfates, etc., away from the steel. So you get a net effect of high alkali, low chloride, and also buildup of alkali phases. This is experimental data that I had way back in the 90s, where this is passing quite a high level current just to exaggerate the effect really and be able to present it graphically. I think it's about 100 or so milliamps per meter squared. You can see very, very clearly that the alkali content increases a lot near the steel, and the chloride content decreases considerably. So you have a net effect of high alkali, low chloride. But even if you're talking about cathodic protection type of levels, that's 20 milliamps per meter squared. That's the top end of cathodic protection, but you still get an increase in alkali concentration around the steel reinforcement. Another piece of work at Imperial College in London showed that you get a benefit of increased resistance to chloride if you do certain things. One was to basically they measured the amount of interfacial void of a certain diameter and higher inside their concrete. So they produce loads of concretes in different ways, different mixes, some with a lot of plasticizer and a lot of vibration to eliminate as much of the porosity as possible. And what they've achieved is, with the better quality concrete, they were able to for the steel to tolerate much higher chloride content, up to about 2.5% of chloride before corrosion had initiated. But they also achieved the same thing by using ordinary concrete, which is that sort of range over here, and electrochemically treating it, i.e. passing a cathodic current to the steel for some months. And they were able to tolerate, again, much higher chloride contents. And they noticed that there was a layer of alkali being produced on the surface of the steel. And this is what they found, really. When they opened up the specimens, they saw where corrosion initiates, and there's a lot of little voids that nothing happens, but this larger voids is where corrosion initiates. And you know that once corrosion initiates, it sort of concentrates in that point. So the purpose of the work was to try and block this pores by producing current, and therefore pushing the current would primarily concentrate in that region, and pushing alkalis into that region to reduce the size of those pores. And this is it schematically, really. What you do when you cast concrete on concrete, you have on steel, you have a fairly consistent layer of lime, Portlandite, sitting on the surface of the steel. That acts as a physical barrier as well as a chemical barrier. But where you've got your potential defects or pores, the chloride can percolate through to it and initiate corrosion. So the idea is to try and block those pores with alkalis that you produce subsequently. So in summary of that, really, the corrosion of steel initiates at defects and voids in the concrete, and it's possible by electrochemical treatment to increase the tolerance of chlorides and so on. Okay. But now, which part of your structure really do you need to protect? I wouldn't suggest that you protect the whole structure. There'll be a huge number of anodes, obviously. So you've got to choose depending on the environment. For example, it could be salt spray. It could be salt carried by cars in a parking lot. It could be driving rain. It could be aggressive environment in the soil underneath and so on. And that's one of the major areas that you need to protect, but also construction and expansion joints. Construction joints actually are quite susceptible. So when you're building your structure, you may want a layer of anodes at every point where you're building a new level of concrete. These are a few examples now, quickly. This is in Italy. It's a road leading to a port, and the worry there was that de-icing salts from the top would settle on top of the piers and initiate corrosion. So here's the construction stage. You can see how much steel there's there before the concrete is poured. So actually, putting anodes all over will be not very efficient. So they looked at the top layer, which they felt was going to be problematic. I would have suggested to them that that area there and the base would also be problematic, but they viewed that as the most at risk. So they put a layer of anodes, this is XP4 anodes, all around the top of the steel reinforcement, and then cast the concrete around it. Now you can see from here that where the expansion joints are going to be, and therefore that is definitely the susceptible area. My view is that the chloride would also run down to the base, and you would have a high risk area at the base as well. And the next example shows that really in Himera Viaduct in Sicily. They now concentrated on the base, on the cap, and where it meets the column, and you can see from that's all the anodes that they've designed to go around the base of the column and around the base of the cap. Again, these are caps, but in this case, because you have a lot of steel in that direction, they chose to use the DAS anode, which are long rods, or now actually long prisms of galvanic anode, and you obviously get better distribution and much higher current as well, because it's a much larger anode. Okay, so I will summarize now. 25 years of data has enabled us to understand the long-term behavior of the galvanic anodes, as I've shown, and based on detailed data, particularly on the current output, the temperature, the aging behavior, we were able to put together a robust design specification and procedure. And as you've seen, the results are really backed up by third-party work. And there I would thank you for your attention and invite questions.
All right, George, excellent presentation. We've got some excellent presentations, or sorry, excellent questions coming in as well, some hard hitters here. We encourage everyone to get your questions in now. If we don't get to them during the show here, we will be passing these along to George afterwards, and he'll do his best to get back to each of you afterwards. And to start us off, we had Joe was asking for computing steel density. Do you count both the top and bottom mats when you're calculating that density within an area?
Okay,
say like in a slab?
It's a good question. Yeah, thanks for that. It depends on how close the steel mats are, really. Obviously, because of the resistance of the concrete, the further away the steel is, the more resistant it is for the current to get to it. But if it's close together, then some part of it will get to that. So I would suggest that if your bottom layer is sort of within 100 or so millimeters, you add another 30% perhaps to the steel density or steel area, because obviously some of the current is going to be diverted to that.
From C. Russo, they ask, as the anode corrodes, does it leave a void behind?
No, definitely not. In fact, what will be the problem, or the suspected problem, will be that there'll be such an expansion that it will crack the anode. Obviously, it doesn't happen in ours. I didn't go through all the details because there isn't enough time. But as the zinc corrodes, it becomes zincate ions, which tend to percolate around the pore structure of the surrounding mortar, the encasing mortar, and then they precipitate out as zinc oxide. So they have the ability to move around, but also settle down whether there's an empty space. And you can see, in fact, one of the slides that I showed, the photograph, was there was a thickness of zinc corrosion product on the surface of the anode that had replaced the zinc that was there originally. But there's more zinc product because it's more expansive, and some of that was able to migrate into the pore structure of the surrounding mortar and settle there. I've got photographs to show you that, but not in this presentation, unfortunately. So there's no gaps developing, and there's no expansion, not sufficient expansion to crack the mortar if you're worried about the other side.
Excellent answer. We got another one here. Are there any guidelines or recommended practices for periodic inspection procedures to check if these anodes are performing as expected? Can these systems be monitored?
If you definitely want to monitor, then a suggestion is that you take a representative patch and do what we do with our trials, and instead of connecting the anodes directly onto the steel, you take the wire out, or you connect it to a wire which is taken out into a monitoring box or a junction box, and then take a separate wire back to the steel reinforcement, or 2 or 3 wires back to the steel reinforcement. That allows the current to flow through the junction box, and therefore you can measure it if you have a resistor in there. If you don't want to do that, the only other way really is to monitor the potential. And what you would tend to see is that there's quite a negative potential once you put your anodes in, and with time that should be going up in an upward direction. And over the years, it could even become almost passive. So there'll be a sign. But unless you divert the current and measure it, it's not really that well. There's some claims that there's a technique that would just by polarizing through the concrete, the anode, you might be able to work out if it's still working or not. I've not used it personally, but that's actually included as a technique, as a monitoring technique, and others that are present in the AMP standard for cathode protection.
All right, then we got time for one more, and then we'll have to let everyone go here. But you showed that all the charts and kind of examples were showing like a standard 20-year service life expectation. Can these systems be designed to go beyond 20 years?
Yep. Again, we tend to standardize everything and say that with these anodes, you are aiming particularly for a 20-year life. Theoretically, you can get longer life than that. We know that the anodes continue to produce current beyond the 20 years. We already know that goes 25 years, for example, and because we can now predict the current output, we know how low it will become towards the end. And all you do is really narrow the spacing to get an extra 5 or 10 years. But that may be that the anode density might become a bit too much. So my suggestion really, if you want to go beyond 20 years, you would need to look, or not need to look, but you're better advised to look at the other range of anode systems that we have, and in particular the fusion anode, which I've not talked about, but I think there's a talk further down the line which concentrates specifically on that system.
And that's a great plug for the next two presentations we have in this series. But I'll get to those in a moment. First, I'm going to talk about George here. So we've got his contact information on screen. If you got any more questions, you can get them in now. We're going to pass these on to George. You can also, with his information on the screen here, contact him after the show with any questions you might have. We'll also be sending out his information with our post-event email, which will contain a link to George's presentation that you just saw, as well as a link to the recording. Coming up next month, is distributed galvanic anode design. So that's what George was referring to, those longer anodes. That's going to be presented by Cheyenne Yazdani from VCS Engineering. So he's going to be talking about how those DAS anode systems are typically designed, and then some of the other use cases, including encasements and in marine pile jackets. And then the fusion anode that George alluded to at the end is going to be part of Dave Simpson's two-stage anode design webinar. This is going to be in June. You can find both of those on our website at wesavestructures.info. So you can find the registration pages for those there as well. If you're not unable to make it to any of those, we recommend even just registering, just so you can get a notification when the presentation and recording go live. But you can again find those on our website here. And thank you all for attending. Thank you, George, for that excellent presentation.
Thank you all for listening.
Awesome. And let's get out there and save some structures. Thank you all for coming.